Welcome to Math Practice. Today we are going to start with Class 12 Maths. To understand the concepts and the solutions to examples, please subscribe to the channel. Today we are going to start with an interesting topic, relations and functions. So watch the video till the end. First we start with the definitions. A relation R is a set of ordered pairs. That means if an ordered pair AB belongs to R, we say that A is related to B under the relation R and we write as A capital R B. See, relations we are going to study with respect to maths, but you have relations in daily life also. For examples, relation of being siblings, relations of being friends, all these are relations. So if there is any relation between two objects, then we can have ordered pairs which belong to that relation. For example, let L be the relation less than or equal to which is defined on the set 1, 2, 3, 6. Then L can contain which type of ordered pairs? 1, 1. Why? Because 1 is less than or equal to 1. Then for example 1, 2, 1, 3, 1, 6, 2, 2, 2, 3, 2, 3, 2 less than or equal to 3. But we cannot have 3, 2 because 3 is not less than or equal to 2. So it will not belong to this set. A relation R in a set A is called an empty relation if no element of A is related to any element of B, and it is denoted by null set. Let A be the set of all students of a boys' school. Then suppose if I define a relation R as A is a sister of B, then obviously it is an empty relation because it is a boys' school. Now a relation R is called a universal relation when if each element of A is related to every other element of A. For example, let B be the set of 3 male children of Mr. X. Then the relation R defined on B given by set of all ordered pairs such AB such that A is a brother of B. It is a universal relation. Why? Because 3 children all are male children, so each one will be a brother of each other. So both empty relation and universal relation are sometimes called trivial relations. Next we are going to study the important different types of relations. Now 3 important types of relations. A relation R in a set A is called reflexive if for every element A ordered pair AA belongs to R. That means every element is related to itself. It is called symmetric if A1 A2 belongs to R implies that A2 A1 should also belong to R for all A1 A2. It is transitive if A1 A2 belongs to R, A2 A3 belongs to R, then A1 A3 should also belong to R. Let us understand by examples. For example, if you have a set X which has two elements 1, 2. On this set X, let us define relation R which has ordered pairs 1, 1, 2, 2, 1, 2. It is reflexive. Why? Because for every element of X, that means for 1 and 2 both the elements, 1 should be related to 1, 2 should be related to 2. So since R has 1, 1, 2, 2 ordered pairs, it is reflexive. Other than that, it can have any other ordered pairs. Now symmetric. Is this relation R symmetric? No. Why? Symmetric means if A1 A2 belongs to R, A2 A1 should also belong to R. So since 1 2 belongs to R, 2 1 should also belong to R, then only it is symmetric. So now if I define R dash relation as 1 1 2 2 1 2 2 1, then it will be symmetric. Next, suppose I have a set X which has elements 1 2 and 3. On this I define a relation R as 1 2 2 3 and 1 3, then it is symmetric. It is transitive. Why? Because 1 2 2 3, so 1 3 should also belong to R. If this is satisfied, then it is transitive. So this relation is called a transitive relation. Now some general examples. Equal to relation, less than or equal to relation, they are reflexive because for any number if I take, I can say a number 2 is less than or equal to 2. So each element will be related to itself. So relations of equal to, less than or equal to are reflexive. But just less than is not reflexive because 2 less than 3, but 3 is not less than 2. So it will not be symmetric also, and it will not be reflexive. Why? Even 2 is less than 2. We cannot write in that manner. So it is not reflexive, it is not symmetric. Similarly, the relation less than, equal to, and less than or equal to, if I take these relations, then they are transitive in the set of real numbers. Why? Why they are transitive? Because first one, say less than relation. So 2 less than 3, 3 less than 4, then 2 will be less than 4. So it is transitive. Equal to, obviously it will be transitive, and less than or equal to will also be transitive. So these are some general examples. Let us take the first example. If S has elements 1, 2, 3, 4 and a relation R which is defined on S is given by R which has ordered pairs 1, 2, 4, 3, 2, 2, 2, 1 and 3, 1. First thing, show that R is not transitive. Now, if I want to show it is not transitive, I should have at least one set of pairs in which A1 related to A2, A2 related to A3, but A1 is not related to A3. That means in this case 3, that means 4 is related to 3, 3 is related to 1. So now 4 should also be related to 1 for being transitive. But do we have 4, 1 in R? No. So it is not transitive. Second case, now since it is not transitive, find a relation R dash such that R is a subset of R dash and R dash is now transitive. That means try to find a bigger relation R dash such that that relation will become transitive. So now 1, 2, 4, 3, 2, 2, 2, 1 and 3, 1. Already it is there in R. Now we want to add some ordered pairs to make this relation transitive. So first thing is, see, I have 1, 2, I have 2, 1. So I should have 1, 1 for making it transitive. So I will be adding the ordered pair 1, 1. Similarly, I have 4, 3 and 3, 1. So I should have 4, 1. So I am adding our ordered pair 4, 1. Correct? Now, what I am having, another ordered pair 4, 3 is there. 3, 1 is there, 4, 1 is there. Yes, check it out, it is there. Correct? Now, if I add now 3, 2, then will it be transitive? Yes, it will be transitive. Correct? Why? Because 4, 3, 3, 2 is there. So 4, 2 should also be there. Then it will be transitive. So again, I am adding 4, 2. So I have found a bigger relation than R, which is now transitive. You have to check with all orders pairs. Second example. Determine whether each of the following relations are reflexive, symmetric and transitive. So now we will get a better idea of the types of relation. First one in this case is relation R on set A which has elements 1 to 6. R is defined as set of all ordered pairs such that Y is divisible by X. What is the meaning of Y divisible by X? That means suppose if I am having 6, then I can say 6 is divisible by 3. 6 is divisible by 2, 6 can also be divisible by 1. So that is called Y is divisible by X. The first thing is try to get all the ordered pairs which satisfy this relation. So try to get the relation R. 1, 1, 2, 2, 3, 3 will always be there. Why? Because every element is divisible by itself. So all first 6 elements are very obvious. Then 1 is divisible by 2, 1 divisible by 3, 1 divisible by all the elements up till 6. Now 2. Is 2 divisible by 3? No, you cannot write 3 as 2 into something. So that ordered pair we will not have. But 2, 4 we will have because 2 is divisible by 4. Similarly, 2 is divisible by 6. And then 3 is divisible by 6. So these are the possible ordered pairs of R. Now let us try to check the properties. First thing, it is reflexive, very obvious because every number is divisible by itself. It is not symmetric. Why? As if Y is divisible by X, it does not imply always that X will also be divisible by Y. For example, we have the ordered pair 2, 4, but do we have 4, 2? No. 2 is divisible by 4, but obviously 4 is not divisible by 2. So this relation is not symmetric. It is transitive. Why? Let us check it out. In general terms, if I say X is divisible by Y, what do I mean by that? X can be written as sum A into Y. Correct? X is divisible by Y. For example, say 6 is divisible by 3. Then I can write 6 as sum 2 into 3. Again, say Y is divisible by Z. Means I can write Y is equal to some number B into Z. So now what is x? X is a into y, but put the value of y. Y is b into z. So now x is some number a into b. It is a number into z. That means if I am having x divisible by y, y divisible by z, then I will always have that x is divisible by z. So this relation is transitive. Remember, this can be defined on any set of numbers. If I am extending this set 1 to 6 instead of 1 to 6, if I am having any 1 to n, then this relation will always be reflexive and transitive but not symmetric. Correct? Therefore, the given relation is reflexive and transitive but not symmetric. Next example. Determine whether each of the following relations are reflexive, symmetric and transitive. In this case, let us take the second example. Relation R in a set of real numbers such that R has ordered pairs of the type A, B, where A less than or equal to B square. First of all, will this relation be reflexive? No. Why? Because A, remember, the set on which it is defined is a set of real numbers. So for every real number, it is not true that you will have A less than or equal to B square, means A square. For example, suppose if I take half, real number means it can contain fractions. So half. So will half be less than or equal to half square, which is 1 upon 4? No. Half cannot be less than or equal to 1 upon 4. So ordered pair of the type half will not belong to R. So R is not reflexive. Remember here, because it is on the set of real numbers, you can show that it is not reflexive. Now R is not symmetric again over here. Why? Because A less than or equal to B square obviously does not imply always that B less than or equal to A square. You can just find any ordered pair. You can give example. Say 1, 2 belongs to R. Why? Because 1 less than or equal to 2 square. But is 2 less than or equal to 1 square? No. So it is not symmetric. Transitive. Suppose AB and BC belong to R. What does that mean? A less than or equal to B square, B less than or equal to C square. Then this will not imply always that A less than or equal to C square. Again, try to get an example to show this. So suppose if I take half and minus 1. Half less than or equal to minus 1 square. Why? Because half is less than 1. Similarly, minus 1 less than or equal to half square. Why? Because minus 1 less than, you can write minus 1 less than or equal to 1 upon 4. So half minus 1 half, both these ordered pairs belong to a relation R. But do half and half belong to R? No, just now we have seen it does not belong to R. So A1, A2, A3 belongs to R, but A1, A3 does not belong to R. It is not transitive. So this relation defined on the set of real numbers is not reflexive, not symmetric and not transitive. Similarly, note that the relation R, which is defined as set of all ordered pairs AB such that A less than or equal to B cube. This is also not reflexive, not symmetric and not transitive. You can prove on the similar terms. Example 3. Give an example of a relation which is, first case, it is symmetric but neither reflexive nor transitive. Remember, you can give any answer. Here we have taken a set S which has elements 1, 2, 3. And on this set, if R is defined as having the following ordered pairs 1, 1, 2, 2, 1, 2, 2, 3, 2, 1 and 3, 2. Then first of all, you want it is not reflexive. Not reflexive means 1, 1, 2, 2 is there but 3, 3 is not there. So it is not reflexive. Symmetric. Is it symmetric? Yes, because 1, 2 is there, 2, 1 is there, 2, 3 is there, 3, 2 is there. So it is symmetric. Is it transitive? No. Why? Because 3, 2 is there, 2, 3 is there but 3, 3 does not belong to R. So it is not transitive. Second case, give an example of a relation which is transitive but neither reflexive nor symmetric. Now this we have seen previously that if you have the relation less than on set of say natural numbers, then we can say it is not reflexive because you cannot write 2 is less than 2. Correct? Can you write it as symmetric? No. 2 less than 3, then 3 will obviously not be less than 2. So it is not symmetric, but it will always be transitive. Why? Because 2 less than 3, 3 less than 4, obviously 2 will be less than 4. So for set of relations, for relation less than on set of natural numbers, you can say that it is neither reflexive nor symmetric, but it is transitive. Third case, reflexive and symmetric but not transitive. Suppose I have defined the relation R in this manner, then this relation is reflexive because 1 1 2 2 is there. So 1 1 2 2 is there and 3 3 is also there. So it is reflexive. It is symmetric, yes, because if I am having 1 2, I am having 2 1 2 3, then 3 2 is also there. So it is obviously symmetric. But it is not transitive. Why? Because 1 2 is there, 2 3 is there, but 1 3 is not there in our R. So R is not transitive. So this type of examples can be given. Next, we want an example of a relation which is reflexive and transitive but not symmetric. Suppose just now we have seen this type of relation. If I am having any set, say A, which has numbers 1 to 6, and what was the relation we have just seen in the previous example, y is divisible by x. Then we had shown that this relation is reflexive and transitive but not symmetric. Fifth case, you want a relation which is symmetric and transitive but not reflexive. See, suppose if I am having the set R which has elements A, B such that A is a brother of B, which is defined on the set of males, then it is not reflexive as A is not a brother of A. Correct? Same person cannot be the brother of the same person. So A is not a brother of A, so it is not reflexive. It is symmetric is as if A is a brother of B, B is a brother of A, then obviously this will always happen because it is defined on the set of males. It is transitive, yes, because if A is a brother of B, B is a brother of C, then A will also be a brother of C. Again, why? Because it is defined on the set of males. Now, an important type of relation, equivalence relation. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. All the three properties have to be satisfied. For example, relation of equality on set of real numbers, obviously we have seen it is reflexive, symmetric and transitive. Same way, equality of subsets, which is defined on the universal set. That means set of all subsets if you take, that will also be equivalence relation. Correct? Remember, subsets means it can be a subset or equal to. Similarity of triangles, this will also always be reflexive, symmetric and transitive, because you know that a triangle will be similar to itself. If one triangle is similar to another one, other one will also be similar to the first one. And if triangle 1 is similar to triangle 2 is similar to triangle 3, obviously triangle 1 will be similar to triangle 3. So these are the examples of equivalence relation. So an overview, you can have empty and universal relation, you can have reflexive, symmetric and transitive relation, and if a relation is reflexive, symmetric and transitive, then it is called a equivalence relation. Now, one thing, important result, note that the total number of distinct relations from a set A to a set B is 2 raised to mn. What is it? Now, suppose the elements, let the number of elements of set A and B be mn respectively. That means A has m elements, B has n elements. Then the number of elements of A cross B, you know, when you take the cross product, it will have elements m into n elements. That means, for example, if A has 2 elements, B has 3 elements, then A cross B will be having 2 into 3 means 6 elements. So, number of elements in the power set of A cross B. A cross B has mn elements. You know that if a set is there, its power set will contain 2 raised to the number of elements of the set. So, the elements of the power set of A cross B will be 2 raised to mn. That means A cross B has 2 raised to mn different subsets. Now, every subset of A cross B is a relation from A to B. Every subset from A to B, every subset of A cross B can form a relation from A to B. So, the total number of different relations possible from A to B is 2 raised to mn. Next important example, show that the relation R, which has ordered pairs of the type x, y, where x minus y is divisible by 3, which is defined on the set of natural numbers n, it is an equivalence relation. This relation is used many a times in maths and it is called congruence modulo 3 relation, and it is denoted as A is congruent to B mod 3. For example, suppose if I am having x as 6 and y as 3, then 6 minus 3, which is 3, is divisible by 3. So ordered pair 6, 3 will be a member of R. So this is the relation R which we are having. First thing is we will check for reflexivity. Suppose if I am having any element A, then A minus A, you know that is 0. So 0 is divisible by any element. So 0 is divisible by 3, hence it is reflexive. Secondly, if AB belongs to R, what does that mean? By definition of R we have over here, A minus B is divisible by 3. So now B minus A I can write as minus of A minus B. So that would also be divisible by 3. So it is symmetric. For example, if I am having say 6, 3, that means 6 minus 3, which is 3 divisible by 3. Then 3 minus 6, that will be minus 3. So minus 3 will also be divisible by 3. So it will always be symmetric. For ABC belongs to N, if AB and BC belong to R, that means A minus B divisible by 3, B minus C divisible by 3. Then can I write A minus C as A minus B plus B minus C? So that will also be divisible by 3, correct? For example, say if I am having 12, 6, that means 12 minus 6 is 6, divisible by 3. Another ordered pair is 6, 3. 6 minus 3 divisible by 3. So both these ordered pairs belong to a relation 12, 6 and 6, 3. Then 12, 3. That will also be 12 minus 3. That will also be divisible by 3. So if AB, BC belong to R, then in this case AC will also belong to R. So R is an equivalence relation. Remember, this is modulo 3. You can have for any number n over here. Now, based on the definition of equivalence relation, we define equivalence class. Given an equivalence relation on a set S, an equivalence class with respect to an element A in S is a set of all elements in S that are related to A. It is denoted by square bracket A. Square bracket A means the equivalence class generated by the element A. It will have which elements? It will have all those elements of S such that X is related to A. Set of all the elements related to A. For example, consider the set of integers Z and the equivalence relation is defined by congruence modulo n. Just now we had seen congruence modulo 3. Similarly, here for any n you have the congruence modulo n relation. In this case, two integers A and B are considered equivalent, means A is congruent to B mod n. When they have the same remainder when divided by n. Actually, let us understand this by taking the next example. Example 5. Let relation R is such that it consists of ordered pairs x, y, where x minus y is divisible by 3. Means it is the congruence modulo 3 relation which is defined on the set of integers Z. You have to find all the equivalence classes generated by the elements of Z. Correct? Your main set is Z, and what is the relation? Congruence modulo 3 relation, means x minus y is divisible by 3. First equivalence class is generated by the element say 0, y. Now what do we mean by equivalence class generated by 0? Means set of all those elements which are related to 0. Now is minus 3 related to 0? Yes. Why? Because 0 minus minus 3, x minus y. So 0 minus minus 3 is equal to 3. It is divisible by 3. So minus 3 belongs to the equivalence class generated by 0. Next is 0. 0 minus 0, yes, divisible by 3. Next element in this set is 3. So 0 minus 3, which is minus 3, that is also divisible by 3. So the elements in the equivalence class generated by 0 will be of this type. Minus 6, minus 3, 0, 3, 6, 9 and so on. Correct? Next equivalence class possible for this relation is the equivalence class generated by the element 1. Suppose if I take minus 2, so 1 minus minus 2, that means 3 is divisible by 3. 1 minus 1, 0 is divisible by 1. Next element in this set is say 4. So 1 minus 4 is minus 3, divisible by 3. So the equivalence class generated by the element 1 by the given relation will have elements of this kind: minus 5, minus 2, 1, 4, 7. Again obviously with the difference of 3. Next will be 10. Third equivalence class for this relation will be equivalence class generated by the element 2. For example, if I take minus 1, the 2 minus minus 1, x minus y, so 2 minus minus 1 is equal to 3 divisible by 3, 2 minus 2, 0 divisible by 3, 2 minus 5 is equal to minus 3 divisible by 3, next is 8. So it will have elements of this kind. So for this particular relation, congruence modulo 3 relation defined on the set of integers, the possible equivalence classes are the ones which are generated by 0, by 1 and 2. 3 equivalence classes are there. One more thing, just note in this that all the 3 equivalence classes are disjoint. That means if an element is there in the equivalence class generated by 0, it will not be there in 1 and 2. So these are disjoint. And the next thing you can notice, if you take the union of all these 3, it will give you the whole set of integers. Like for example, you have 0, 1, 2, 3, 4, 5, 6, 7, 8. Correct? In this way it will go on. And here on this side, minus 2, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6 and so on. So the union of all these 3 will be the whole set of integers. Now in general, suppose if I want to write these equivalence classes, correct? Equivalence class generated by 0. You can also say it is equivalence class generated by 3, but because it will also have the same element. So it is of the kind 3r for any integer r. Equivalence class generated by 1. It will have elements of which kind? 3r plus 1. Correct? For any integer. For example, if r is 0, it is equivalence class generated by 1. If r is 1, it is equivalence class generated by 4, 7 and so on. Same way, equivalence class generated by 2 will have the elements of the type 3r plus 2 for all integers r. Next, different kind of example. Show that the relation R defined in a set A of all triangles as R is equal to set of ordered pairs T1, T2, where T1 is similar to T2. That means it is the similarity of triangles relation. We have to show it is an equivalence relation. Previously, if you remember, we had seen that it is reflexive, symmetric and transitive. So that means it is an equivalence relation. So that is very simple. Now next is consider 3 right triangles T1 with sides 3, 4, 5, T2 with sides 5, 12, 13 and T3 with sides 6, 8, 10. Which of these are related? So first part is you have to show it is equivalence relation that we had just seen previously, because every triangle is similar to itself. If T1 is similar to T2, T2 is always similar to T1. If first triangle is similar to second, second to third, then first will also be similar to the third one. So it is an equivalence relation. Second part, suppose if T1, T2, T3 are right angled triangles, it is given. We know that two triangles are similar if their sides are proportional. So now here if you check, then here you are having 3 by 6 is same as 4 by 8 and that is same as 5 by 10. Correct? So T1 and T3, they are related. Why? Because the sides are in proportion. Example 6. Let L be the set of all lines in xy plane and R be the relation in L defined as R has the ordered pairs of the type L1, L2 where L1 line is parallel to line L2. First is show it is an equivalence relation. Second thing is find the set of all lines which are related to the line y is equal to 2x plus 4. Now first thing, it is obviously reflexive. Why? Because any line will be parallel to itself. Second case, if the first line is parallel to second and then second line will obviously be parallel to the first one. So if L1, L2 belongs to R, L2, L1 will belong to R. Third case, first line parallel to second, second line parallel to the third line, then first and third line will also be parallel to each other. So R is transitive. So it is an equivalence relation. In the second part, we have to find the set of all lines which are related to the given line y is equal to 2x plus 4. Related means what is the relation in this sum? It is parallel. So we know that two lines are parallel if and only if they have the same slope but different y-intercept values. Correct? You know that two lines are parallel if that obviously their slope has to be same. So y is equal to mx plus b where m is the slope, b is the y-intercept. So if you take any line such that the slope m is same but b value is same or different, any value, then it will be parallel to the given line. So the set of lines parallel to y is equal to 2x plus 4 will be given by y is equal to 2x plus k for any k belongs to R. 2 should remain the same, slope should remain the same. So friends, in the first part of this topic, we have covered the different kinds of relation and examples based on that. In the next video, we are going to see a very important topic, functions and different kinds of functions. So subscribe to the channel and do like and share the video.